In March of this year, a UFO was allegedly spotted over the town of Buga, Colombia, zigzagging through the sky in a way that defies the movement of conventional aircraft.
One morning near Buga, Colombia, a small metal sphere crashed into a field. Local officers secured the site and moved the object into locked laboratory storage. Early tests surprised technicians when a focused particle beam changed readings around the sphere.
Object now known as the Buga sphere, a mysterious flying sphere recovered in the town of Buga, Colombia.
Scientists then paused public testing and prepared detailed laboratory work to learn how the object responded to energy and to record every measurement. But when the energy readings began to spike on their own hours later, scientists froze. Was the sphere somehow alive? Where it landed, Buga and the recovery. The object landed in a rural field near Buga, in the Valle del Cauca region of Colombia. People reported seeing a bright flash in the sky and then a small metallic ball on the ground. Neighbors called emergency services. Officers from the Buga Municipal Police and staff from the Municipal Environmental Office arrived at the scene. They cleared the area and kept bystanders at a safe distance. First responders checked the immediate area for hazards. They looked for spilled fuels, strong smells, or loose material. Medical staff interviewed witnesses for possible exposure symptoms. The responders took pictures and marked the exact location with GPS so the position could be logged. Officers placed a temporary barrier around the find to stop curious people from touching the object. Authorities contacted regional scientific bodies and university experts for assistance. Researchers from a nearby university agreed to advise on safe handling. The first formal step was to move the object into a sealed container. Workers used gloves and non-metal tools to avoid leaving fingerprints or contaminating the surface. The container was moved only by people on the custody team. Each person who handled the object signed a record. At the receiving laboratory, staff began a strict logging process. Technicians wrote the date, time, names of handlers, and the source of the sample. They photographed the sphere from many angles under controlled light. The lab measured the object with calipers and weighed it on a digital scale. They recorded surface temperature and ambient room conditions as part of the initial file. Operators used basic non-invasive tools to check the object.
To present initial scientific findings surrounding the object now known as the Buga sphere.
They took high-resolution images and then ran X-ray scans to look for internal cavities. The first X-ray images suggested a dense interior without clear hollow spaces. Technicians also used a handheld magnet to test the magnetic response. The object did not show a strong magnetic pull. Specialists swabbed the surface and kept the swabs for later chemical tests. The laboratory set up strict storage for the sphere. Staff placed it on a padded, non-conductive stand inside a locked cabinet. They logged room temperature and humidity on an environmental sheet. Surveillance cameras recorded the storage area at all times, and access keys were limited to authorized staff. These steps preserved the condition of the object for later checks at larger facilities. Officials issued public statements to explain that experts were working and that safety protocols were in place. The laboratory limited media access to protect test integrity. Journalists remained near the perimeter while technicians continued with the step-by-step procedures. Police maintained a guard while the object remained at the laboratory. After initial checks, the laboratory prepared samples and documents for transfer to national facilities for more detailed analysis. Those steps followed standard evidence handling procedures. The chain of custody paperwork moved with the object, so every transfer recorded who had the sphere and when. That track record made it possible for multiple labs to examine the object in turn, without confusion. All first-day steps focused on safety, documentation, and controlled testing. The goal was to gather clean data and preserve the object for deeper work at larger centers that could run advanced scans and chemical analysis.
When scanning the surface of the sphere, the engravings do not appear so that we can scan them.
Officials arranged secure transport to a national laboratory equipped for detailed work. Teams planned scheduled handovers and agreed on the tests to run. Those steps aimed to make sure every result could be checked again by other qualified teams using standard laboratory methods and maintain full transparency across institutions. But before anyone could even describe its true nature, one question lingered in every mind. What exactly was inside? How the sphere looks and feels. The sphere looked like a large metal ball. Technicians measured it carefully. They used calipers to find the exact width and a digital scale to weigh it. The object was about the size of a heavy bowling ball. The finish had a low shine that did not reflect like chrome. The surface felt cool when touched with a gloved hand. Close inspection showed a line of repeated marks on one side. The marks formed short straight strokes and small circles. Researchers took many close-up pictures to capture each mark. Specialists examined those pictures at a magnified scale. Under a stereo microscope, the marks showed fine tool marks around their edges. The pattern suggested deliberate cutting or engraving rather than random scratching. Technicians ran a simple hardness test in one small area that did not affect the main markings. The test used a standard hardness file to see how the surface resisted a scratch. The metal resisted light scratching and showed a hard outer layer. The result told researchers that the surface had a strong finish or coating. A handheld elemental analyzer gave a first read of surface metals. The device listed common elements found on the outer layer, including aluminum and titanium, and traces of other metals. Later, a mass spectrometer at a university laboratory gave more exact results. That instrument separated atoms by weight and measured their amounts. The mass spectrometer report showed a combination of metals that did not match a common household alloy. To see inside without cutting the object open, technicians used X-ray imaging and a computed tomography scanner. Those scans revealed a dense interior with areas of slightly different density. Imaging did not show batteries, wires, or hollow spaces. The interior looked compact. Small patches appeared darker or lighter, which suggested different metals or tightly bound layers. They measured temperature change over time. They used a surface thermometer and an infrared camera. Under normal room conditions, the object remained a little cooler than the surrounding air. The cooling pattern held for many hours and did not change with normal handling. That observation showed that the object did not absorb room heat quickly. Sound tests gave more clues. Technicians tapped the surface at several points and recorded the tone. The tone stayed low and did not ring like thin metal. The sound profile matched a rigid, dense object. After beam tests, the team would repeat the sound checks to look for any new resonances. A swab of the surface went to a chemistry lab for analysis. The swab checked for organic compounds, fuel residues, or environmental materials from the fall site. Results returned with normal dust, pollen, and tiny amounts of common corrosion. No biological material or explosive residue appeared on the swab. Magnetic tests used a strong magnet and a magnetometer. The object did not show a strong attraction. The magnetometer measured only small and variable magnetic fields around the surface. Electrostatic probes measured charge differences when the object moved. Those charges disappeared within seconds when the object grounded.
A nearly identical object appeared in Yumbo, Colombia.
Conductivity checks used probes placed across several surface points. Some regions conducted electricity well. Other areas showed poor conduction. The uneven conductivity fits the picture of layered or treated surfaces. The measured electrical response helped technicians plan later tests that probe how electricity and heat move through the material. Microscope work included scanning electron microscopy at a national laboratory. That instrument revealed grain patterns and microstructure in the outer layer. Small crystalline patterns suggested a manufactured process rather than casual corrosion. Electron microscopy also allowed energy dispersive analysis to show elements at small scales. Radiation checks used Geiger counters and gamma spectrometers. Readings stayed within normal background levels for known ionizing radiation. The team kept monitoring during all handling and planned more sensitive checks at the national lab. All samples and images received labels and secure storage. Each test report included the instrument used, the name of the technician, and the exact time of the measurement. Those details created a detailed record that other teams could follow when they joined the analysis later. The laboratory kept a strict log so that later researchers could reproduce each step with the same tools. But if every test so far showed nothing unusual, what would happen when the object faced direct, concentrated energy for the first time? The particle beam event and lab findings. Technicians set up controlled tests to see how the sphere reacted to directed energy. The tests used a beam of particles aimed at the object from a short distance. A particle beam is a stream of small, charged pieces of matter sent at high speed. Labs use beams for material research and to study how surfaces change under energy. The testing area had shields, sensors, and safety limits to protect staff. In the test sequence, operators increased beam power in steps. The team watched how the sphere reacted after each step. Instruments recorded temperature, light emissions, electric currents, and any change in mass. The first responses were small. The sphere warmed slightly where the beam hit. At higher beam power, staff reported a larger change. The instrument logs showed a sudden decrease in the reflected energy detected near the object. The beam that hit the surface did not come back the same way. Operators recorded that more beam energy seemed to move into the object. During and after the beam exposure, several instruments recorded unusual readings. An infrared camera showed a rapid cooling of the impact area within a short time after exposure. A power meter recorded less energy in the reflected path than in similar tests with common metals. An electrometer showed a transient current that flowed in the nearby grounding systems. Technicians recorded minor vibrations in the object detected by accelerometers. The CT images taken after the beam test showed small changes in the internal density near the impact site. Lab staff measured the mass of the sphere before and after the beam tests. Scales used by technicians are precise to small fractions of a gram. The reports noted slight mass differences that fell within the margin of error for the instruments. Technicians treated those mass shifts as uncertain and gathered more data. Later, they ran repeated beam pulses while monitoring the object for a range of effects. These tests aimed to see whether the initial readings repeated under controlled conditions. Repeated sequences helped the team separate random error from repeatable response. To understand what absorption might mean, labs tried to measure the energy budget. They compared the beam energy sent from the source to the energy that left the scene on the detectors. The difference showed energy that the instruments could not account for in the reflected beam and in the heat. Some of that missing energy matched short bursts of electromagnetic noise recorded on sensors. The noise appeared as short pulses across a wide range of frequencies. Technicians also detected low-level radio frequency signals that occurred at the same times as the beam pulses. Scientists ran tests to see if the object had become electrically charged or magnetic after the beam exposure. Magnetometers found no permanent magnetization. Electrostatic probes recorded brief charge changes that dissipated quickly. A conductivity test measured how well electricity moved along the surface. The sphere held good conductivity in several regions and poor conductivity in others. That uneven pattern matched the CT images that showed layers with different material properties. One lab found that when the object received focused particle pulses, a tiny area near the impact point showed a change in hardness. A hardness tester recorded a small increase in surface strength at that spot. The change suggested a local alteration in the metal structure from the beam energy. Another test exposed the surface to sound waves and then scanned for new resonant frequencies. The resonance pattern shifted slightly in areas affected by the beam. These shifts gave scientists more data to model how the object might rearrange energy inside. Lab technicians also monitored for radiation by using Geiger counters and spectrometers. Readings stayed within normal background levels for common gamma and beta radiation. The results reassured staff that the tests did not produce dangerous ionizing radiation under the conditions used. The labs followed standard safety limits and paused any experiment that produced unexpected spikes in readings. Based on the test sequence, technicians concluded that the object interacted with the beam in a way that changed some measured properties. The changes were not consistent with simple melting, burning, or breakage. Instead, the data pointed to local material changes and temporary electromagnetic effects. Technicians collected all logs and prepared detailed reports. Those reports included raw measurements, timestamps, and instrument calibration details so others could repeat and verify the tests in larger facilities. Beams in material tests are often made of electrons or protons. Electron beams add charge and heat. Proton beams carry more mass and can change material in more direct ways when energy is high. Operators choose beam energy and pulse length to see effects. In this case, teams used short pulses that pushed energy into an area. That kind of burst can change the metal structure without simply melting it. A larger agency then took custody of the object and suspended open testing. The suspension meant that no outside tests would continue until a central team approved the next steps. The object moved to a secure lab. Staff there planned detailed chemical and isotope tests to check whether the beam had changed the atoms in the object. Planned work included mass spectrometry to measure element amounts and isotope ratios. Labs also planned neutron activation analysis to reveal hidden elements. Another tool was a synchrotron X-ray beamline that can show crystal structure and tiny internal features. Each test shows how the material is built and how it reacts. Scientists also planned to repeat beam exposures under controls. Multiple teams at labs would run the same tests to confirm results. Possible explanations for the observations include a special alloy, a layered coating that traps energy, or a dense internal arrangement that changes how energy moves. Researchers collected all data so experts could compare results to refine models. But as the data poured in, one pattern kept defying logic, something the instruments couldn't explain. What were scientists missing? What scientists say, and what might explain it? Scientists examined the test reports and data to form explanations. They grouped possible reasons into three plain categories. The first category covers material makeup. Some metals and alloys behave strangely when hit by focused energy. A layered or graded alloy can trap energy at an interface between layers. That trapped energy shows up as local temperature or structural change without melting the whole object. The second category covers surface treatments and coatings. A special coating can change how a surface interacts with charged particles or heat. The third category covers interior structure. A dense arrangement of parts inside an object can move energy away from the surface and into internal channels. Experts realized that a change in how energy moved through the object could explain why less reflected beam energy returned to detectors. If the beam energy moved into internal modes or electrical currents, instruments that only measure reflected light would read less return. That pattern matched some measurements from the controlled tests. Researchers also pointed to the way pulses were delivered. Short, high-power pulses can push electrons and heat into new positions in a solid. Those shifts may increase local strength, while also creating temporary electric effects. Other possible explanations involve engineered materials that are not common in everyday items. Materials known as composites combine layers or fibers with different properties. Composites can show odd responses when energy hits at certain angles. Another possibility is a manufactured object built to hide sensors or electronics inside dense packing. If sensors or wiring are present, they might move or rearrange under a beam and then return to a stable state, leading to transient readings. To test these options, scientists proposed a set of experiments. First, they would run a full elemental analysis using mass spectrometry and isotope ratio checks. That would reveal unexpected elements or changes in the atomic mix. Second, they would use electron microscopy to see small features on the surface and inside microsections. Third, they would expose the object to controlled particle pulses at a national facility and compare results to the initial tests. Fourth, they would test the object at extremes of temperature to see how it responds to cold and heat. Experts also emphasized repeatability. A true physical effect repeats under the same conditions. If another lab can reproduce the same absorption pattern, scientists can move from observation to explanation. Scientists planned to share calibrated instruments and test sequences so teams could compare results precisely. That collaboration helps remove errors caused by instrument setup or human error. Beyond physical explanations, some experts considered practical safety and legal steps. They recommended limited public access during major tests to keep people safe and to protect the chain of custody. They also advised that any unusual findings be submitted to peer-reviewed processes so other scientists could examine the data. Peer review does not deliver final answers quickly, but it does build consensus. The possible outcomes of these investigations ranged from normal to surprising. One outcome would show that the sphere is a manufactured object built with a known alloy or coating. Another outcome would show a novel material with uncommon responses to particle energy. The rarest outcome would record a new physical effect that scientists had not seen before. Each outcome requires careful proof. Scientists plan to move step by step, using tests and shared data to reach strong conclusions. If confirmed, the finding could significantly influence material design, sensor technology, and safety procedures worldwide. So, what does this mean for the legacy of Archimedes? Could his lost designs, reborn through quantum intelligence, reveal technologies centuries ahead of their time? What if this is only the beginning? What other secrets might still be hidden beneath layers of ink and parchment? The past may not be gone. It may just be waiting to be reactivated. Let us know your thoughts in the comment section. And don't forget to like and subscribe to get more amazing videos.